start over here. Let us take a look the real world problem. What we have here is a product. Okay, it's a product called composite column. This composite column has the section like this. The orange circular thing over here is the steel tube. Okay, and this is the reinforcement, and they're going to pour the concrete fill to the column. So there is three things. One is the hollow steel section, another is the rebar cage, another is the concrete. This column is very good in load bearing capacity. What is called is going to take a large load compare a typical reinforced concrete, and it has very high fire endurance or fire resistance, and it can assemble very fast during construction. And if you consider this column will compose of one is going to be the orange steel cage, and the second one is going to be the reinforcement, and then it's supposed to be a straight line. You fill up this with the concrete. Okay, these three types of material going to work together in the real world. The force will apply to the top of this, and the force distributed to all the material. And what happens is all the material going to help to resist the force. This is P due to the concrete. This is P due to steel. This is P due to steel. And this is P due to steel. Okay, and then there is the P due to the concrete, and the last one is going to be the P due to the tube. Okay, and if you do the summation of x sub x equal to 0 based on this real world model, all the force gonna have to pass into the centroid of the structure. Okay, the centroid of the material. They are coincide to each other. So this is automatically correct. And the next one, if you do the summation of the moment on the centroid of the section, the equation gonna be automatically correct. So you got the last one that we have is the summation of f sub y equal to 0. And if you set this is positive, you have P of the steel rod and P of the concrete and P of the steel tube. That is going to be, for example, the force of 1,000 kilonewton. What happened is you have 3 unknown. Now there is 3 unknown, and then you have no more equation of equilibrium. What you need to know to solve this kind of problem, this is going to be the next lecture that we are going to talking about. And let me say, if you like to solve these 3 unknown, you got to have 2 more equation. And what is going to be the equation? That is going to be the compatibility condition. You got to find this compatibility condition 2 more. Okay, where the compatibility condition come from? That is going to be the main topic that we going to cut. But the compatibility condition will come from the deformation of the structure. Okay, what kind of deformation? You see the column, when column subjected to the force, what happened is the column will shorten. Since the force applied to the centroid of this column, the deformation that occur here gonna be this one, and you may say the deformation of the concrete is equal to the deformation of the steel tube, or you may say the deformation of the concrete equal to the deformation of the steel rod. Okay, that means you can have two more equations based on the consideration of this deformation of the structure. This is an important thing when we talking about this kind of structure, statically indeterminate. Why? Because you cannot solve this problem by only consider the equation of equilibrium. You got to find more condition. In this case, you find the compatibility condition, and you got two of them, and then the material must be in the linear elastic. Okay, so what you have over here is going to be the P concrete. You have what? P equal to PL over AE L concrete divided by A concrete and E concrete equal to P2. Okay, L2 divided by A2 and E2, and then that is going to be equal to P of the steel, L of the steel divided by A of the steel and E of the steel, and then you may have two more conditions used to solve this problem. Okay, and I like to say that the statically indeterminate axial load member, such as the column here, they have a lot of application. Okay, it's maybe in the form of concrete filled hollow section, as you see here, or partially concrete encased section. That is going to be here, and the concrete encased section, this is going to be here. Okay, there is at least three type of thing, and it can be designed based upon this European Union condition. And then this is going to be our topic. From now, we cannot solve our problem only using the free body diagram and using the equation of equilibrium. You got to determine the compatibility condition to assist, and we call this kind of structure statically indeterminate axial load member. And there is a lot of things about this thing. This is another example that's going to use the composite column in various type of building. And very strict, we didn't use much in Thailand, but this kind of structure used a lot in the developed country. And this kind of thing also one of my research topic with my student. Okay, we have this one is the RC column. The RC column have this kind of behavior. What is called is RC column have low strength, and then we put the concrete. Okay, we put the concrete and steel and encased by this steel tube. This is going to be the steel tube. We test it in our lab. We found that when we increase the thickness of the tube, okay, this is 3.2 thickness of the tube. This is no steel tube. This is 3.2 millimeter thickness, and this is 4.5 millimeter. And you can see if the steel case is steel tube is thicker, the graph will get taller. That means they can take more forces by putting the reinforced concrete in the steel tube or making it as the composite column. Okay, and there is another type of this kind of statically indeterminate. If you can see, this is fixed. So this is going to be B sub y, and this is going to be B sub x, and it's going to be M sub x. And also, you see the two force member over here, they're going to produce the force of F sub AB. So in this structure, you have four unknown, and you have only three equations of equilibrium. This structure is statically indeterminate. Okay, you need one compatibility condition, but this kind of problem is harder. Okay, so we will study this kind of statically indeterminate structure later. For example, the civil engineering student will study this one in the theory of structure on the next class. Okay, and you can find this kind of structure at the Department of Civil Engineering, Konkan University. It's my school. And later we will talking about this, but I let you guys know this structure has unknown larger than the equation of equilibrium, and then you got to find this compatibility condition. It's going to be harder. Previously, we just set the column to have the equal settlement, but for this one, when you consider this one, the deformation, the point A will move over here, and then the beam will have this kind of deformation, and then the rod AC will increase its length, and then we got to consider over here, it's going to be delta SA. That's occur in the rod, delta SA in the rod, and it's going to be delta SA of the beam. That means you got to determine the deflection of the beam, and you don't study this one yet. You're going to study this one in the, if I correct, in the chapter 11. We're going to study the deflection of beam. So later, next course, we will have a chance to visit this kind of statically indeterminate structure. For the now on, the problem is going to be something like this, going to be easier, okay? But before you can do this, you got to consider the structure separately. For example, for this one, you got to consider the deformation of the rod, and then you got to consider the deformation of the beam. If you go to the previous example, you got to consider all the deformation, and then you got to consider them as the compatibility equation. And by doing that, we are going to use this another important principle. It's called Principle of Superposition. Okay, and this one again bases on the linear elastic behavior of the structure, and the deformation must be very small. And what is said, the total displacement or the resultant stress at a given point of the member is equal to the summation of the displacement or stress due to each F pilot. What happens is, if you like to determine the deflection of this beam, okay, due to the 8 kilonewton and 2 kilonewton, this principle, okay, allow you to separate this beam into two beams, one subjected to uniformly distributed load, another one subjected to 8 kilonewton load, and then it's going to be easy for you if you go to the chapter 11. You have a deflection table. You can determine the deflection for each case, and then you can combine them. And this is based on the principle of superposition. The V sub C equal to V sub C1 plus V sub C2, but determine the V sub C directly is hard. We got to separate to be the easier one and combine them to each other. Another example will be based on the moment. For example, if you like to find the moment diagram for this beam, you separate this beam into three cases. One, 5 kilonewton per meter. Another one, 20 kilonewton meter moment on the left. And another one, 20 kilonewton on the right. And then there is the moment diagram table. For this one, it's going to be easy to find like this. For this one, you got this one. For this one, you got this one. And then the final result is going to be this one. By what? Putting this one 0, minus 20, and this one 0. So this is minus 20. 90. This is going to be minus 10. This is going to be minus 10. So you got this one 70. And this one is 0, 0, and minus 20. This is minus 20. So you just draw the curve, and then you get the moment diagram of this one. So the principle of superposition simply allow you to separate the beam, the structure that's subjected to this one, three different kind of loading into the simple case, and then you combine simple cases, and then you combine them together, get the result. No matter it's the deflection, or no matter it's the moment, and no matter it's the stress or the strain. You can use this one. Is very important one. And why we cannot use it if the structure have large deformation? Example, if you have this P equal to 10 kilonewton, and this P1 is going to be 6 kilonewton, and this P2 is 4 kilonewton. And then what we have is, under the application of the force, what we has over here, under this one, this is large force. If it's produce large deformation, is maybe 0.7 meter. This is a small force. This one maybe 0.8 meter. And this one smaller is going to be 0.9 meter. What I'm saying is, if the if you consider this one, if the force is large to produce very large deformation, this is going to be 10 kilonewton. And then this, the horizontal distance reduced to 0.7. Okay, but when you apply a smaller force, 6 kilonewton, this is maybe 0.8. And if it's 4 kilonewton, this is 0.9. And what happened is, the combination is not follow what it's supposed to be. Okay, this is going to be 10 times 0.7 is what equal to 6 times 0.8 plus 4 times 0.9. So it is the obligation, it is the regulation to set the deformation must be very small, okay, very small, in order the length of this T picture are equal. For example, if the deflection is very small, okay, it's going to be the same length. When it's going to be the same length, the D1 equal to D2 equal to D3, and let's say it's equal to 1.0 meter. Based on this is going to be 10 times 1. That is going to be equal to 6 times 1 plus 4 times 1. That is the meaning of small deformation to be the assumption, to be the limitation to use the principle of superposition. Okay, next, I just explain about statically indeterminate. We start by what we has known before, statically determinate structure. Okay, consider this one from the engineering static. We will draw the free body diagram, and then we start by setting the reference axis. Let's say if this has 1 kilonewton weight, we like to know the force in the T sub in the AB, in the cable AB, and T sub AD. By doing this, when you draw the free body diagram, just take the A over here, and then what we have, the 1 kilonewton will be in this direction, and then the cable gonna have the force. One is going to be T sub AD, another one is going to be T sub AB, and then what we have is, this is the ratio, right? 45. And next step, you just draw the ratio that you have. This is 4, this is 3, this is 4, this is 3. So this is going to be the free body diagram. And then you use the equation of equilibrium. By doing this, during the summation of x sub x equal to 0, you just take the component of this one, and you can see this is going to be T sub AB times 3 over 5, and this one also, sorry, this is just AD, this is T sub AB 3 times over 5. So these two are equal. T sub AB equal to T sub AD. Okay, this is the first one. And then when you take the summation of the force in the vertical direction, you have this one, T sub AB times what? This is 4 over 5. And this is T sub AD 4 over 5. Okay, and summation of f sub y equal to 0. T sub AB times 4 over 5 plus T sub AD times 4 over 5. They are upward. Okay, that means upward is positive. That is equal to 1.0 kilonewton. So you can solve for the T sub AB and T sub AD. This is a kind of statically determinate structure. You can analyze by using the free body diagram and the equation of equilibrium. However, for this one, you cannot do it, because from this one, you will have 3 forces in the equation. For example, if you again draw this one as the A, and then this one is the X, and this one is the Y, and 1 kilonewton force here, and the force in the cable, number 1 is here, and number 2 is here. This is T sub AB as before. This is T sub AC, and this is going to be T sub A D. What happened is when you take the summation of the f sub x, you got one equation the same as before, because this ones will be separated into T sub AB times what this is 3 over 5. This is going to be T sub AD times 3 over 5. So summation of x sub x equal to 0. T sub AB equal to T sub AD. However, when you do the summation of the f sub y, and then f sub y equal to 0 upward. So now you have T sub AB times 4 over 5. This is going to be the component here. T sub AD the same thing, plus T sub AD times 4 over 5. But now you have T sub AC, and then that is going to be 1.0. You cannot solve these two equations since there is 1, 2, and 3 unknown. You got to use the compatibility condition. What is going to be the compatibility condition of this? This problem going to be a little bit harder. You got to have this movement from this one to this one, and then you consider the relationship of the deformation of this rod. and then that's deformation going to be the deformation of the AC, is equal to the deformation of the AB and equal to the deformation of the AD. This coefficient must be determined by using the trigonometry, but it's not in the form of force function. You got to input the deformation by this equation. So the next equation will be the form of the equation in the unknown forces, and you can solve 3 equations, 1, 2, and this one 3 to get the solution. This is a kind of example to show you about the statically indeterminate compare with statically determinate. Now we move to the step that I did show you. First, consider the structure by draw the free body diagram. And for the statically indeterminate structure, the unknown will be more than the equation of equilibrium. Then you just write the equilibrium equation, and then you write the compatibility condition. By writing the compatibility condition, you consider the deformation of the structure for the column. They are going to have what? The shortening with the same length. For the beam, the deflection of the beam equal to the deflection of the rod. From the 3 cable, all of the cable will based on the movement of point A to A prime, point A to this new one. This is due to 1 kilonewton. This one going to be A prime. All of this will have one common variable, and then you plug the force displacement relationship, to get this one. And that is over here. This is the compatibility, the shortening of the column and the steel. They are going to be the same. For this one, the C will be the C prime. So the AC will change to A C prime, and the BC will change to B C prime. And then you can say this one, the C slash A, the deformation of this top portion is going to plus the deformation of the bottom portion, the deformation of this one, this is going to be shortening, this is going to be elongation, the C over B, and then they are, when combined, is going to be 0. This is going to be elongation. This is going to be contraction. Okay, combination is going to be 0. You got to consider the deformation of the structure. And then this compatibility condition is in the form of deformation. You got to use this equation to change this compatibility condition in the function of the force. Then you have enough equation. You solve the simultaneous equation to obtain the unknown forces. Then you can determine the stress, you can determine the strain, you can determine the stress later. This is a kind of step involved. And this is going to be the midterm examination. If you guys go to the example that I just posed to you. Okay, let's start with the simplest one. You have what? You have this kind of structure. Let's say you have this one, like a rubber band, and then let's fix my finger on the top and on the bottom. Okay, and then there is a force occur over here trying to move it. Let's see this force just put it down. When put it down, you can see the green rubber band get elongation and the red rubber band get contraction. This is a kind of deformation of this structure, and you will use this one to write the compatibility condition. And if you do it, okay, that is the force occur on this finger, and is the force occur on this finger due to this one. Okay, if you understand this kind of problem, it's going to help you to solve this one. First, draw the free body diagram, and then we will count the unknown. How many do we have? This is going to be the column. Let's say this is going to be the column, and then this column has the fixed support, okay, at A and B. So when this column subjected to force passing to its centroid, okay, even though this is the fixed support, the force reaction occur at A and B going to be only the axial force. Okay, don't worry, guys. We are for first 4 chapter we involve with this kind of structure, and the beam, the other structure will be later. You will find this kind of structure in truss, in column, in pylon. Okay, that's an example that we use. And what we have is the F sub A gonna be the reaction. The F sub B gonna be the reaction. If you consider the force passing to the centroid of the column, this automatically correct. Okay, there is no horizontal force. This is automatically correct. There is moment occur on this column. Only one going to be summation of F sub Y equal to 0. If upward is positive, F sub A plus F sub B minus, they are upward. Okay, minus P is 0. See, you use all of the equation of equilibrium, but the number of unknown is more than the equation now. You have 2, that is going to be F sub A and F sub B. Okay, for example, if you may set P equal to 10 kilonewton, and then you need more equation to solve this statically indeterminate column. Okay, and then you got to again consider the deformation of this column, consider under the force, and to consider the deformation of the column, you got to draw another free body diagram, okay, of the member AC and of the member BC. Just draw it. You can see since A and B is fixed, no movement. My hand cannot, my finger cannot move. Only the column can move. Okay, and then you got to draw this one. And for this one, F sub A will produce this F sub A inside it. Okay, based on this, you may say summation of F sub Y equal to 0. This one, you may say F sub A C equal to F sub A. And it is tension. This is going to produce the elongation. And the other one on the bottom. Okay, again, the force passing to this, you do the summation of F sub Y equal to 0, F sub BC equal to F sub B. Okay, by doing this, I can say this equation, this portion that I put it in the left is going to be delta at this point C with respect to this one, to A. Okay, and then plus another one that is going to be on this bottom part. Okay, subjected to the compression. This is going to be the delta at what? At point C with respect to this one B. They are going to be 0. Okay, and you may just write it. The deformation of point A with respect to point B is won't change. It's always has the same length of L, maybe 4 meters. It won't move. Only point C move. Okay, and this equation is in the form of deformation. This equation is in the form of force. You're going to change the deformation to be the force by force displacement relation. You have this one from the previous lecture. And now, this is going to be F sub A. Okay, the red one is going to be this one. Is going to be F sub A, and then this portion is L sub AC, the length, and divided by A and E. This means all the column have the area of A, both portion, and has the same modulus of elasticity E. So you consider the next one, the second portion is in compression. That's why they change this symbol from positive to negative. And then this subject to F sub B, L sub CB, okay, and then AE. Now you may cut these two and rearrange this equation. You will get F sub A. Okay, you just put this one, you get F sub A, L sub A, C equal to F sub B, L sub CB. Now, F sub B will be equal to F sub A, L sub AC divided L sub CB. This is going to be number 1. This is going to be number 2. Okay, if you plug this F sub B into this equation, you will get F sub A, L sub AC divided L sub CB plus F sub A equal to P. And then you rearrange it, you will get the solution of F sub A. in the form of the force P. Okay, and then you just plug this one back into this equation, and then you can solve for the F sub B. You can do it by yourself. Okay, it's your assignment to go back for self-study. Then you can find the stresses, you can find the strains, and you can find the deformation of this structure. Okay, now let's come to a number that is going to be in the symbol format, and it's hard to understand. This problem is a little bit thicker because the column AB, the lot AB, the AB over here. The AB, let me put it in the red, is going to be made by aluminum, and then it has 400 millimeter ring, and then the yielding stress and the modulus of elasticity of the aluminum is here. Okay, and it also has 10 millimeter diameter, or you may D sub A C equal to 10 millimeter. So when you have the problem, please carefully read it. Then you have the steel for the portion BC, and for the portion BC is going to 800 millimeter long, and it has the diameter. This is D sub BC of 8 millimeter. So this is smaller than the aluminum. And then it has the property like this. This is yielding stress. This is the modulus of elasticity. What special of this one from the previous one? There is a gap over here. Okay, this gap is 1 millimeter. This gap going to involve with the compatibility condition. So be careful on this. Previous example, there is no gap. Okay, this one, there is a gap. And then you will see this one will go to the equation for the compatibility condition. Let us start by finding the reaction at the A and B. Okay, to determine this, you got to draw the free body diagram of this lot. Okay, of lot A, C, B. Now you draw this one, and then you got to check. You got to check. We under the application of the force. Okay, this member, this aluminum member, okay, will get the elongation. Why? Because if you cut all of this one, and then you draw the free body diagram, this force of 20 kilonewton, it can move freely, and it will cause this F sub A. Okay, this reaction at point A. How about this? If this end won't touch B palm, okay, there is no force. Let's assume, okay, over here is going to be the free end first, and we're going to consider the deformation of this portion AC. If it's larger than 1 millimeter, this B will touch B palm, and it will produce the reaction at B. And the problem is going to be statically indeterminate. But if the deformation of this portion is smaller than 1 millimeter, okay, this won't touch, and the problem going to be statically determinate. Okay, so we're gonna check the total deformation. When we check the total deformation again, we're gonna cut this one and draw it free body diagram. This one, you may say summation of x sub x equal to 0. So based on this, F sub A is going to be 20 kilonewton. So the field body diagram of the member AC, this is going to be 20 kilometer, and this is going to be F sub AC. Again, summation of x sub x equal to 0. F sub AC is 20 kilonewton. Now the deformation of this actually is supposed to be C/A. It's going to be C/A. Only this portion, okay? This portion, if you cut based on the assumption, if you cut over here, there is no force. So this has no deformation. So just plug this one. F sub AC is 20 kilonewton, and this is going to be 400 millimeter. This is 0.4 meter, and this is the portion of AC. The portion of AC has this one. The area is pi times this one, pi r squared, 5 millimeter square, and then you get this one in millimeter square. So you got to take 10 minus 6 to change it to meter square. And this is aluminum. E is going to be 70, 10 power 9 Newton per meter square. This is a Newton. So what is important to taking care of the unit. And then you got the C/A to be 1.46, okay, and this is going to be the deformation of B/A. The movement C, if C is movement for 1.46 millimeter, this one will move for 1.46 millimeter also, but this is larger than 1.0 millimeter. That means point B will touch the wall, okay, and then the structure is statically indeterminate. Okay, let's check if P equal to 10 kilonewton. If P equal to 10 kilonewton, the structure will be statically determinate. Let you guys work on this. Okay, let's P equal to 10 kilonewton. If P equal to 10 kilonewton, the structure will be statically determinate. This one will be half of this. Okay, 1.46 divided by 2. That is going to be 0.70 millimeter, less than 1 millimeter. The structure statically determinate. Since this one is statically indeterminate, go to the previous one. The knowledge from the previous one. Okay, the force going to occur at D palm. Since the deformation is larger than 1 millimeter. And again, the 20 kilonewton force point to the right. All right, the reaction will resist point to the left. And then summation of F sub x equal to 0 and summation moment equal to 0 automatically correct. Okay, you may set the summation of F sub y equal to 0, the summation of moment equal to 0 automatically correct. Since the force passing to the centroid of the section, okay, forces pass through TROUGH centroid C of section. Okay, that's why. And then summation of x sub x equal to 0. Okay, you get minus f sub a minus f sub b. Since you put this one in the positive, it's going to be plus 20,000 Newton. And you have only one equation again. the compatibility condition. Now, this one will not be zero as the previous one because this one has the gap. Okay, so you just put the gap into the compatibility condition from the previous one. Okay, and then you draw the free body diagram of this portion. Again, summation of f sub x equal to 0, f sub ac equal to f sub a. And then if you cut over here, summation of x sub x equal to 0, f sub bc equal to f sub b. Okay, f sub bc is inside it. And then you use the force displacement relationship based upon what we have. This is going to be in tension and this is going to be in compression. When it's in compression, it's going to get contraction. When it's in elongation, it's going to get tension. And then for the tension, the deformation going to be positive. For the contraction, the deformation is negative. And then you just plug the load displacement relationship. F sub A is over here. F sub A. And this one is L sub AC. Okay, and then it's going to be A sub AC. Previously, you have it. And aluminum and negative minus F sub B. L sub BC is going to be 800. And the A sub AC is going to be computed from the previous one. And then just plug everything in. Check the unit. You get this equation now. You have this one for number 1. You got this one for number 2. You have just 2 unknown. You can solve it easily by what? Solving the simultaneous equation is up to you. Then you get F sub A of what? Of 17.01. And F sub B is 2.99. If you check with the summation of x sub x equal to 0, okay, it's going to be in equilibrium. Okay, this one plus this one is going to be 20. Now, the axial stress, okay, the axial stress just divide the R sub A or F sub A, the force inside this member by the area, that is going to be less than sigma sub y of actually aluminum. And for F sub B is less than sigma sub y of the steel. You can conclude they are linear elastic. And when they are linear elastic, that means the condition that we use on this one is correct. And then you can further to calculate the deformation over here to check this point is going to move to C palm. What is going to be? Okay, that is going to be delta C slash A or delta AC. And then that is going to be 1.24. This one is 1.24. How about this one? This point going to move for only 1 millimeter. Okay, that means the BC will shortening for 0.24 millimeter. Okay, this is the one of the first type of statically indeterminate. Okay, and let me give you another example before we break it. This is the second type. The second type is the composite column that I told you before. However, there is aluminum tube, and that means tube. Tube is mean the section gonna be something like this, and then there is the brace core. Okay, that is going to be in this area. That is going to be brace. Okay, the outside. outside. This one gonna be aluminum. They give us this column with 0.5 meter. Okay, it said under the force of 40 kilonewton. Okay, that's passing a stiff bearing plate. That means by putting the stiff bearing plate, the force distribute to the aluminum and brass uniformly, and the deformation gonna be equal. They said find the stress in the aluminum and the brass when aluminum has E equal to 70 gigapascal. The base has 105 gigapascal. The same thing. You got to start by draw the free body diagram of the whole structure and check whether it is statically determinate or indeterminate. By doing this, the 45 kilonewton will resist by the force of the aluminum, and that's distributed symmetrically about the centroid of the section, because the force always on this chapter 1 to chapter 4 passing to the centroid of the section. And then you have this one for F sub AL. Both of them. Not this is F sub L. It's the combination of these two arrows is F sub AL. So summation of X sub X equal to be correctly, automatically correct. Summation of moment also. So only the summation of F sub Y. So upward is positive. F sub BR plus F sub AL, okay, is going to be equal to 45 kilonewton. And what happened is you use all of the equation of equilibrium, okay, and you have two unknowns to solve. This is 1, this is 2. You got to have one more condition. That means you consider the deformation of this one. Okay, if you put this one into dimension and then you dog it under the force, the column shorten, the aluminum and the brass shorten with the same distance. Okay, so you may say the deformation of aluminum equal to the deformation of the brass. And then really simple, right? From the previous one, if I change this one to the concrete and the steel, you can do it. And then just put everything, the F due to the aluminum, that means this is F aluminum. The L, all of them have the same length, okay, the brass and aluminum, and A aluminum and E aluminum. And I could tell you the aluminum will have this kind of section, okay. You may determine A sub AL equal to pi. This is going to be 50. That is 25 square. This diameter, inside diameter 25 is going to be 12.5 square. This is going to be the area of aluminum. Okay, it's hollow section. So you got to use it. Sorry, I'm wrong on this. This is going to be 50. Okay, this is going to be 50 by on this, and this is going to be 25. Okay, pi r. This is r sub o. This is r sub I. This is going to be 25.0. Okay, that is wrong. So beware about this. And the inside, the core of this, okay, the A of BR is going to be very easy. Pi times this one, only this one, pi times 25 millimeter square. Just put them and then beware about the unit that you use. Now, this is going to be the coefficient that relate the force in aluminum with respect to the force in the brass. Okay, just be very careful on this. You get what? You get the force in aluminum is 2 times the force in the brace by putting them work together. Okay. Why? Because aluminum is pretty big, the area. Okay, the area. But anyway, just put this second equation, put into the first equation and solve it. You get F sub BR of 15 kilonewton, and then F sub aluminum 2 times. That is going to be 30 kilonewton. Now you must check whether it's going to be linear elastic or not. So sigma sub A aluminum, sigma aluminum pi 30 kilonewton R square. Pi, no, 30 kilonewton divided by R square. And the force in the brace is 7.64. All of them less than sigma sub Y, and they are in the linear elastic. And if you do the distribution of stress, this is important. Okay, you will see the stress occur in the brace called larger 7.64 megapascal, larger than the brace in the hollow aluminum section 5.09 megapascal. Okay, even though the force in aluminum is larger, but the stress must be divided by the area. Most of the time, this one has the modulus of elastic of 105 megapascal, and this one has the modulus of stiffness of 70 gigapascal. This one indicates the stiffness. Okay, when you put a stiffer material base to work with the less stiff aluminum, the stress in the stiffer larger E will be larger than the stress in the less stiff material. That is one of the conclusions you're supposed to have. And remember how to set up the compatibility equation. Now we have at least 2 types of it. Okay, the first one separate into 2 types, and this is going to be the third one. And then what the column going to be shortened? Can you compute it? Okay, you just plug everything into your equation. You may pick up one of this. You may pick up this equation, and you can compute for the shortening of this column. Or if you don't like it, you may use this one because they are equal. Okay, no matter the equation is going to provide the same solution. Okay, let me do a little break on this for 5 minutes, and I come back for more problems, and we will finish this chapter today. Okay, guys, I just come back. From this problem, you guys may have the beam ADFB, okay, and you have 2 lots. In the middle of the beam, I show you over here with the green and the red, okay. The problem is asking us to determine the stress in the green, the CD, and in the red, okay. Over there is a wire. In my demonstration, it's just the rubber band. Okay, just come and take a look again at this one. What happened is, actually in the class, I need a guy to help me, hold me, but you may see when I put the force, okay, near the red band, the beam, very stiff beam, will rotate with no deformation. Like I told you, guys, it's going to be something like this. This means what? This means the red wire gonna have larger deformation compared to the green one. Okay, the one that's near the force. The force is over here. So following this, you may understand the deformation of this structure. And you see, this is the pin over here. It's going to be the pin. And then that pin is going to be the rotating point. They give you a lot of information of the wire CD over here. That is its property. And wire EF, which is aluminum. This is aluminum. This is steel and different cross-sectional area. And based upon what I show you under the force, okay, the rotation of the beam ADFB will be changed from this horizontal line to this new one. You got to do the same thing. Draw the Fibonacci diagram of the beam ADFB and check what the unknown that you have. So the A is going to have, this is pin. So you got to have A sub X and A sub Y over here. This is wire. It's the same as the rubber band. Okay, the force is only in the axial force, T sub EF and T sub CD. And then you may use the summation of the moment about point A to eliminate the A sub X and A sub Y from our consideration. So just take the moment at this one first, because we like to find the stress as the YCD and YEF. That means before you find the stress, we got to find the force. Okay, from the force, we can find the stress. We can find the stress that they asked us to do. And then you have summation of F sub what? This one, summation moment, sorry, about A, because then the moment is going to be what? This is going to be counterclockwise. Let's say if it's counterclockwise is positive, T sub CD gonna time this one, T sub CD gonna time 2 meters, T sub EF plus gonna time 4 meters, and then 20 kilonewton negative is opposite to this direction, 20 times 6. So that is going to be the first equation. Then you can reduce this one by divide by 2. Okay, so reduce 2 T sub CD plus 2 T sub EF. And then this one is only 6 times 10. It's going to be 60. This is the first equation. Then the compatibility condition that we like to have. This is two unknown. We have one more equation. Only one not enough. We got to have 2 equations, one more equation. Like I tell you, like I show you, the deformation of the beam will change from the horizontal line to the inclined line. And then over here, there is the deformation of the cable CD. And the other one is going to be the deformation of the cable EF. We can find the relationship between them. Okay, so the compatibility condition always come from the deformation. You must use the deformation of structure to determine it. By doing this, we use the similar triangle. We just use the similar triangle. Okay, by considering what kind of similar triangle. You see, the delta sub EF, delta sub EF divided by this length, delta sub EF divided by this length is what? 4, right? And then that is going to be delta sub CD divided by this. So equal to delta sub CD divided by 2. Okay, that's CD divided by 2, delta sub EF divided by 4. You can see the deformation of this delta sub EF is 2 times of the delta sub CD. And then you got to use the force displacement relationship to change this compatibility equation to be the function of force. So the delta sub CD over here is going to be T sub CD, okay, time is length of 2 meters, and then this must change to meter square, and this is going to be in the, if you use kilonewton, this is going to be kilonewton per square meter, this is square meter, this is kilonewton, this is meter. So beware about the unit, okay, and then you move to the second one over here. You got to have T sub EF, okay, you have the T sub EF, and then this is 1 meter, just put this one in meter, and then the area just change to meter square, and then aluminum has 80, this is kilonewton per square meter. So again, this is going to be kilonewton per square meter, so beware about this. You put this one back into this equation, put this one into this one, and then rearrange it. You just get the T sub EF. T sub EF. T sub EF is going to be the red one. T sub EF here is going to be 3.2 times T sub CD. So just plug this one back into the equation of equilibrium, rearrange it, you get T sub CD and T sub EF, and check it's going to be 3.2 times or not. If it's correct, it's going to be 3.2 times. And then the stress, no, you can find the reaction also. You got this one for 8.1, you got this one for 20.95. So now you are able to what? Determine the force summation of x sub x equal to 0 and a sub x equal to 0. Summation of f sub y equal to 0. You got that one is positive. Okay, a sub y, this is positive, minus 8.11 minus 25.95, and then 20. You got this is 14.06. Okay, and then this is going to be the reaction that we get. You can find the normal stress in the Y, CD, and EF easily, and it must be less than yielding stress. This is going to be linear elastic. Okay, linear elastic, and then they are all linear elastic, and then you can determine all the deformation that occur here by using the same equation, the force displacement relation. Okay, for the delta sub CD, just divide T sub CD by 1,000. That is going to be 0.81, and then you will know this one automatically. It's going to be 2 times by the compatibility condition. Okay, you don't need to compute this one. You may go back to the compatibility condition over here. Delta sub EF is 2 times delta sub CD. You don't need to. Okay, you just answer it. Delta sub F is 2 times delta sub CD, and then you get 1.62. Okay, and then you may find at the B by this one. You got to do the similar triangle. This is 2 meters. This is 2 meters. and this is 2 meter. This is going to be 0.81 millimeter. This one 1.62 millimeter. For this one is going to be 0.81 times 3. That is going to be millimeter. Similar to angle 2.43 by doing this. Okay, and then they may ask you, since A is the pin, can you find the diameter of the pin A if the tau allowed is 55 megapascal? And then this is chapter 1. Yes, we can relate every chapter together. Okay, since this is going to be what? This is in the form of double shear. This is double shear. So the resultant force will divide into half of 7.03. And then you have tau equal to V over A. Now, you like to determine A, so it's going to be V divided by tau allowable. You get it for 12.8 millimeter. Okay, if they don't ask you to increase the size to buy it at the store, you don't need to say it's going to be 13 millimeter, 14 millimeter. You cannot select 12. Okay, so select the bigger section when you design the structure. Okay, and then come to the next one. This is going to be a most complicated one, let's per se, and it's close to the examination of the previous year. We teach you like this, and we offer you the problem to solve as the one that I just showed you. Okay, and try to think about using your knowledge. That means using the skill to solve it. You have this kind of knowledge, and you need to apply this knowledge to another kind of problem. They are going to require the same knowledge and skill, just changing in the problem. And then, why don't you give us the example as you showed in the example? No, we cannot, because in the real world, the problem always not the same. Okay, coming to this, the beam ACF, that is going to supposed to call the rigid beam. Okay, it's supported by 3. This lot, all of them made by steel and subjected to 15 kilonewton force in the portion of AF. Okay, they ask us to find the axial force in the steel rod. So we're going to draw the free diagram of the beam ACE, and the force in the lot. All the rods are two force member. So the free body diagram is going to be like this. Basis upon this, you may set this is X, this is Y, 1, and then draw this one. This is going to be step 2, and then put the force. This is going to be step 3, and put the unknown force. Okay, and then you put the dimension. That is going to be the free body diagram, and use the equation of equilibrium. This is for the beam. Summation of x sub x equal to 0. This is automatically correct because no force in x axis. Okay, and then you have 2 more. Summation of f sub y equal to 0, and summation of moment equal to 0. The first one. Summation of f sub y equal to 0, f sub a plus f sub c plus f sub e. Okay, and then minus 15. That's it's going to be 3 unknowns. And then you summation of the force. Let's see, take the force as c, and f sub a rotate in this direction by times 0.5, and this is going to be the opposite one. So the side of these two forces gonna be in opposite direction. So F sub A reverse this direction. So minus F sub A times 0.4 and plus this is going to be counterclockwise, the same direction here. And then this 15 will be rotate the same direction of F sub E. So it's gonna have 0.2 with the positive. You got only two equations. You have 3, 1, 2, 1, 2, 3 unknown. So you got one more equation. Okay, you have two equations here unknown. We cannot solve this problem. What is going to be? It's going to be the force. See, if you guys has the beam and you have the rubber band, just put the rubber band into this one, and if you try to pull it, and it's hard for me for this class. I don't have friend to help me. Let's say it's going to be something like this, and then the force. Actually, on the left and on the right, they have the same lot, and on the middle is what. See, if you put the force in this direction, it's gonna move this thing. It's gonna move this thing. It's gonna move because the force that near the lot, will move. I mean, I don't have hand to show it, but you can do it like this. Okay, the force over here will push this section. The one will have force over here move downward more. So that has to show you guys. Just have friend working on this. So what's supposed to be is the deformation, the displacement of the beam ACE supposed to be some kind of this. Okay, the movement in this direction must be more than in this direction because the force is over here. And then by doing this, the compatibility condition will be something like this. If you said this is going to be delta sub E, and previously this is going to be the delta sub A, and let's say this is going to be the delta sub C. You will see by doing this, the portion of delta sub C, this one going to be delta sub E, and this one also going to be delta sub E. So what we have left over here, that is going to be delta A minus delta E, and also what left over here is going to be delta C minus delta E. And then if you go back to the previous example, you're gonna divide this one by similar triangle. This one divided by 0.4. And this one, let me put it in green. This one will divide by 0.8. So by similar triangle, okay, you may have this one, this green divided by 0.8, this red divided by 0.4, and rearrange the equation, you get this one. Now, it's not in the form of force, okay? It is our duty to what? To use the force displacement relationship, and then just be very, very careful on this and put everything together. You get this equation. That is the third equation now. The problem is harder to solve 3 simultaneous equations to get 3 unknown. It's your duty. And then you just get the forces. You can check it by summation of F sub y equal to 0 or not. Okay, it must be equal to 0. So the tensile stress, very easy. The displacement, okay, you may find one and you use the same relationship. For example, if you prefer to determine the delta sub c, that is going to be, this one is going to be f sub c times the length 0.5, and then the area a sub c d over here, and this is E, okay, of the steel. You get this for 0.577. Then we ask you further what is going to be this one, okay. You may do the computation, or you may just use the similar triangle to determine delta sub E, to determine the delta sub A. Okay, I left this one for you guys to do the computation by yourself. Now, we have another O examination. We have a stick beam again, and it's supported by the column, and the column made by the aluminum. Okay, and then this is aluminum, and the author, they made by the steel, and is subjected to 150 kilonewton per meter. Okay, and this structure, if you seek it, is symmetry. They ask us to find the axial force in the column. So the symmetric structure, the problem over here will different from the previous one. I'm showing you over here because, again, 1 year we teach you the previous example, and another year we use this one as the examination problem. A lot of students just confused, okay, didn't notice that this structure is symmetry. And then what it means is the beam is going to go in the same equal displacement. The deformation that occur usually, what I'm meaning is usually it start over here, okay, due to the symmetry of the force, okay, all of this will have the same shortening over here, and over here. Now, again, you do the free body diagram and you get the force, okay, the force in the steel due to the symmetry on the left and on the right, they must be equal. So this problem is going to be easier than the previous one. There is only two unknown, the force in the steel and the force in the aluminum, but there is two force in the steel, okay, and only one force in the aluminum, and summation of f sub y equal to 0. Summation of them must be 90,000. Then compatibility condition, like I told you, okay, the shortening of the steel is equal to the shortening of aluminum. So you just cut everything together. You may get the relationship between the force in the steel equal to 1.216 of the force in the aluminum, and then you plug it in over here. You will get, so the solution, the force in aluminum gonna take 26.22 from the portion of 150 kilonewton, and force in the steel is like this. Okay, I just give you this one to you because I like to have an idea. That's why what the type of we modify the problem. It's not that hard, but let's read the problem statement carefully and think a little bit before start your work. Okay, and then there is one thing about the temperature, but usually it won't be the examination for our midterm examination. So this is a kind of extra knowledge, okay? But some students from civil engineering, even though the mechanical engineering student, these are important because when the temperature change, okay, when you heat up your structure, the steel will expand, aluminum will expand. So in the road pavement, they provide the expansion joint to let the pavement move due to the temperature change in the midday, and in the midnight, the structure cool down, it will shorten back. So this expansion joint is going to be needed for some kind of structure in order the structure to perform properly. Thinking about the machine, okay, in the truck, in the car, when the engine has combustion, there is forces during the you drive the car, and when you park the car overnight, everything cool down, okay, so the material get shortened. So as the engineer, you got to design this kind of car to taking care of temperature changes, okay, and when the temperature change, the material expand. When the temperature increase, okay, if the temperature decrease, it's going to shrink, and the relationship between the deformation of the material is equal to coefficient of thermal expansion times the change in temperature and length. And the coefficient of thermal expansion, you can take it from the right column of this table. And then this is just to show you if the structure is free, okay, this has the free end. When the temperature change, this free end can move freely. There is no stresses. So temperature changes are important for statically indeterminate structure. Okay, for the statically determinate is okay. The free end can freely move. But for this one, when temperature change, no, on the left and on the right, they don't let the structure move, and that will cause the force inside the member. So you got to be aware about this. And the most simple one, just consider this problem. When we start, the temperature is 30, and due to somehow the temperature change to 60, this column fixed at A and fixed at B, that means it cannot deform. Okay, A and B still 1 millimeter. What is going to be the axial stress in this column? Okay, if the section is 10 millimeter by 10 millimeter, it's just 1 centimeter. Okay, and then the steel is going to be the material, so it's going to be the alpha of the steel. The free body diagram is the same from the first example, but the force occur going to be equal. Okay, and then what we have, F summation of F sub y equal to 0. The force reaction must be equal. Okay, and then what we have is compatibility. The deformation may occur, but the sum of them must be 0. So the deformation due to the temperature must occur due to the alpha L delta T. Okay, but it must be suppressed by the fixed support. So the deformation delta T minus delta F is going to be 0. Okay, to control by the fixed support, and then the delta T, that is going to be the expansion. Okay, it's going to be alpha L delta T. but there is the shortening. That is shortening due to the axial force of resistance of F. So it's going to be FL divided by AE. The F is equal. So the equation of F is going to be 7,200 Newton. That is pretty large. It's only 1 millimeter, and it's 1 meter long. And the temperature change only 30 degrees Celsius. Thinking about you put the rod in the sunlight during the midday. Okay, that is going to be the force. And the stress is 72 megapascal. Even though it's less than the yielding stress, but that is quite a lot. Okay, compared to the sigma allowable, which is going to be 250 divided by 2, that is 120 megapascal. So this is the important thing. Okay, and there is the also problem. I like you guys to go through it, and you may read it by yourself. The same thing, this one have the gap. Okay, you got to check when the temperature change from the 120 to 125, this gap is closed or not. If it won't close, it won't be statically indeterminate. Okay, it won't close, it's only statically determinate. The problem is going to be very easy. But if it's cross the gap by the temperature change, there is the forces. But this time the forces are not the same because the material are different. So when you summation of the force, okay, you got to set summation F sub ST and F sub AL, but they are going to get the same result of F. And the compatibility from the previous one is 0. This one gonna be 1 millimeter. And then you just put this one for the steel. Okay. The previous one you have only one material, so you have only one. And this one for this one for the aluminum, and they must be equal to the gap. Okay, and then just plug off this symbol with the given data. Okay, this is yielding stress, and then you will get this force of 112.68 kilonewton. Again, it's pretty large because this is 100 increase, 100 degrees increase in temperature. So the stress now is approaching the yielding stress for the steel. And then there is the other example. Okay, this is the one, but this one harder than before. Is involved not only the this is the previous one. Don't worry, this one I did tell you already. Okay, this is the previous one, but we can modify this one to involve with the temperature. Okay, without the load, we start with 20 kilonewton, and later the structure have 80 degrees Celsius. The principle of analysis of this problem is going to be the same. It's going to be symmetric structure. Okay, and don't worry, this won't be in the examination, but it's some extra knowledge you got to know. And by doing this, the force 150 kilonewton applied with the change in the temperature. Okay, two things occur at the same time. And again, the force in the steel must be the same because due to the symmetry of the structure. So you got this equation as before. But the compatibility condition, even though they are going to have the same shortening before, but this time there is the temperature to involve in this problem. So it's going to be harder before. In the steel, again, there is two things. One is the change due to temperature. that is going to what? To make this one up, okay? And they said the downward is positive, so this one up gonna be negative. And then they suppressed by the force, okay? Suppressed by the force. And that is for the steel column on the left and on the right. And for the aluminum, the same thing, the same final position occur. But this time there is the deformation due to the temperature, and another one deformation to the force is in the opposite direction. Temperature trying to move the column up, but the force move it down. So you put everything together, okay? The deformation of the steel equal to deformation of the aluminum, and then you get this one. So the hard part is putting everything together like this. Be careful. And you got two equations to solve for the force in the steel column and the force in the aluminum column. You can get this one easily, okay? That's the extra knowledge. You may have it. And this is the end of chapter 4.